So we'll uh, so hi Anand. So we will start today's class within a few minutes. Okay. So please wait. I think the screen is visible to you. So let us start today's session. So first of all, I would welcome all of you to this live interacting session. So this is our final live session, and after that we will have another session, which is based on the concept which we have discussed till now. So this concept is quite important because the concept that we are going to discuss is based on the heat exchanger, and it finds a wide range of application in industries. So before this, let me introduce myself. I am Niloy from IIT Bhubaneswar, a PhD scholar, and regarding these courses, the course instructor are Professor Chakraborty and Professor Shom. I hope that all of you have enjoyed these courses. The way both these professors have taught in that is quite interesting, and even for us, even for the TA like us, whenever we have gone through such types of high detail course where they have explained each and everything in detail, that will definitely help us. And I suggest all of you please go through these courses precisely, and even the live interacting session that has been taken by me, please go through this because I have explained about a lot of question regarding these courses which may be helpful for you in terms of the exam, because the assignment that has been given in the classes, that is different from what has been explained by me in these classes. So I hope that if you have gone through this assignment and this live interacting session, that would be quite easy for you, and it will help you to answer this question in the class. Main thing is that the approach is essential, and how you have gained the basic from these courses, that is quite essential. Okay. So already you know why this courses is essential, and how, like in the today's classes we will be discussing about this heat exchanger. So this heat exchanger you will find in industrial application, in refrigeration system, and everywhere you will find this heat exchanger. So that's why studying this is course is quite vital. So already we have discussed about this conduction, convection, and now in the heat exchanger we will be dealing with both these types of conduction and convection. Along with, we have discussed about the single phase convection and two phase convection, which is basically your boiling and condensation. That thing we have also discussed, right? So your exam is knocking at the door, and it is on the 25th April. So if you are preparing for this exam, so the first suggestion is that go through the fundamental concept. So though there is derivation, and most of the student finds this derivation quite hard. So my suggestion is that you just try to remember the approach, starting approach. If someone of you forgot how to derive this, but if you know this approach, that I have to know this thing, I have to do after there is a derivative term, then I have to integrate. So that is okay. You will get sufficient marks from this question. At least partial marking is there. So that's why studying this concept from the base is quite essential. So in the last classes, we will discuss about an interesting topic, which is this boiling and condensation, right? So this boiling, and if I come to know this what boiling, so this boiling finds an application in the last classes. One of you told that the boiling finds application in heat exchanger, mainly this boiler, right? So in this boiler, how this boiling phenomena is happening, that thing we have discussed. Right now this boiler is also type of heat exchanger, so we will discuss about the various types of heat exchanger and its application, and why these types of heat exchanger is used and for which purpose. So that thing we will discuss today. So before starting, whether you have any issue regarding this previous classes lecture, please let me know. Any doubt? Anyone? Okay, so we are starting with the today's session. So first is the heat exchanger. So the from this term it is quite easy to understand that there is a exchange of heat between something. So what is this thing? Actually it is the exchange of heat between two fluid. So heat exchangers are devices where there is a exchange of fluid between two fluids. But the condition is that what is the property of this two fluid? So definitely as there need to be heat transfer between them, so these two fluid needs to be at different temperature. If these two fluids are not in different temperature, whether there will be heat transfer possible or not? No, it will not be possible, right? So coming to this application, as I have told that if you see in your household life, like many of you have AC in your household life, and also in the winter we are using heater. In both these heat exchanger devices are used. How? Say what is the in the heater there is an heating element, right? So the air is also a fluid, we know. So this air when comes in contact with this heating element, so it gets heat up. So one fluid is the heater, one fluid is this air. The next fluid is the fluid that is helping the element to heat up. That is the heater element. So there are certain pipes. You can observe that in heater there are certain types of pipe. Have you observed this thing, Ayush? So in this pipe, though this pipe looks like this, the inside this pipe generally there is liquid flowing. So that liquid have higher temperature compared to our atmospheric condition or room temperature. As this, I am talking about in heater, room heater. So as this hot water passing through this element, what will happen? It transfer the heat to the surrounding cold air, which is also a fluid, and because of this, the cold air takes up the heat and its temperature increases. That's why we feel warm in front of this heater, right? So that is the phenomenon. This is also type of heat exchanger. So any device, irrespective of the shape, size, you forgot about the size. So see, many students have a misconcept that heat exchanger should be like this. There should be a pipe, there should be an inlet, there should be an outlet, something like this, right? So that is not the scenario. Actually it can be different. The main concept is that there should be two fluid and the heat exchange is between these two fluid. Like if I talk about human body, I am just giving an example. In the human body there are veins, right? Right or wrong? These are veins. So what is flowing inside this vein? Blood is flowing inside this vein. Okay. And what is outside? in our body? What is outside? There is like calcium is there, potassium is there, like other elements. Also, it is a fluid, not blood. See, the in the blood we means RCV, WBC. You have studied. I think you forget this thing. Platelet is there. Also, platelet is there. So, but in the main thing is that blood is flowing through this vein, right? Outside there is also some fluid. So, if the blood is flowing, and see, I am just giving you. If you this is your hand, okay. So, in the hand, if you are moving through this hot, what I can say, in a summer day, just you think that you are going outside, and you are in a you are just wearing a half shirt, so your hand is exposed to atmosphere, right? So what will happen, the temperature, you are feeling the temperature, right? So in other word, if you are feeling this temperature is moving to your hand. So that's why sometimes in high temperature, if the outside temperature is higher, people may get you have here sunstroke. You have heard this word. So, what is this phenomena? If I just give you a little bit hint, not the exact phenomena. So, if because of heat, this heat moves to this blood inside this vein. So, what will happen if something is getting heated up? It's what will happen? It's my question is that if something, some liquid is getting heated up, what initially happens? So if say this is a layer, if we are applying heat, the surrounding liquid, what will happen? What will happen to the surrounding liquid? Temperature will start to rise. After that, what will happen? Just think and tell. Huh. Not always. Boiling will happen only if the blood achieve temperature more than the surface temperature. Right now. So forget about boiling. Just tell in the fundamental concept. If the surface is getting, if the nearby liquid is getting up, what will happen to its density and pressure? Temperature decrease. Density. Okay. Just a minute. Just I am. Let me see whether there is any photo I get from. So you just observe one thing. So if this is vein, so what is outside? Say skin. Forget about other mucus or like types of element. So if this is vein, this is your vein. So there is fluid, and this is your skin. I'm just drawing the skin with another color. So this green one indicate your skin. Okay. So in general condition, just tell me which one is colder and which one is hotter. In general scenario, what is the purpose of our skin? Inside it will be hotter, outside it will be. Huh. So that means, in other word, I can say that if somehow the temperature of the blood increases, like you see during our fever, Uh, so that's why, because as the temperature of the blood increases, it transfer the heat to whom? To our skin. So if it is supplying the heat to our skin, that's why we see that our body temperature rises. Okay. Just a minute. कौन सा वाला चाहिए? जाइए. Hmm. So the thing you get, so that's why our skin temperature increases, right? So in the summer season, already because of the outer atmosphere, if the skin temperature increases, okay, so this blood temperature is already, you know that generally our body temperature is 36.5 degree or 36.4 degree something, right? So if somehow the outer temperature is 40 degree, so at this case what will happen? The heat from outside will move to the blood, because at that time the blood is the cold fluid. Okay, so so in that case the reverse phenomena is happening. That means our body is taking extra heat. So if our body is always is in a neutral mode. So if in a neutral body, if you are giving certain amount of heat from outside, what will happen? Its organ will started to behave in a wrong fashion, right? So that's why what will happen if see in our heart, if I talk about our heart, so certain temperature is there, our heart will take only blood up to certain temperature. So if the temperature is more than that, so the heart started to create problem. That's why people get this stroke. Okay, sunstroke. Or so that's why it is quite advised to these young fellows, like uh, do not go to the outside if the outside temperature is quite hot. For 5 minutes it is not an issue. So if you are staying outside for 1 hour at even at high temperature, and there is no shade above your head, so that thing is quite irritating for our body. So be careful because physics is also there. So now you got the reason why people got this sunstroke. So our body is also a heat exchanger, where the nerve act as the, it's like our pipe. It's like the pipe of a heat exchanger. Okay. So I am moving to the fundamental concept of heat exchanger. So generally, if I talk about heat exchanger, there should be at least two fluid required, right? So there are this type. If I talk about the type of heat exchanger, generally it is a shell. Okay, in a shell, if this is a solid pipe, hollow pipe through which liquid can flow. Okay, and outside this is inlet. This is your outlet. So the thing is that if the fluid is flowing in this direction, let me represent it in a red color, so that you understand that it is a hot fluid. The red indicate hot fluid. So the hot fluid is flowing through this region like this way. Okay, and in the outside is a shell. In this shell, this cold flowing is flowing. So you see, this cold fluid is flowing in which direction? The both the direction of the fluid is in the same way, right? So if in certain cases, this is known as, the outside is known as shell. This is known as tube. Okay. So the configuration is known as shell and tube heat exchanger. Shell and tube heat exchanger. So one type of fluid is flowing through inside the tube and another is flowing outside the tube. Okay. So the thing is that if the fluid is flowing inside the tube, that is also known as tube side. If someone say tube side, that is basically inside the tube. And outside the tube, that means shell side. Got it? Outside the tube, what is outside the tube? It is the shell. So the liquid is there in the shell. So that's why it is known as shell side. Please remember this thing. People get confused. What is shell side? What is tube side? Now, this is an heat exchanger. So parallel flow, counter flow is there, but I will come into this later moment. Another two types of heat exchanger is there. If I talk about this, say these are tubes. Okay, these are certain tubes. So sometimes you will see certain types of plate are there, like the radiator. You see the radiator in a vehicle. In even in the bike engine, you see that outside there is fin structure, right? So that thing basically is a heat exchanger. How it is in heat exchanger? Say through this pipe, the oil is flowing. Oil of a engine is flowing through this pipe. Not oil. I am talking about the fuel. Okay. So if this is flowing through the fuel, that means fuel is a high combustion liquid. So that means its temperature is quite high. So this fin arrangement, what will happen? The air is blowing outside. Because of this air and fin, I know that the fin is helping us to transfer heat effectively. So the heat from the inside the tube is initially transferred to the plate, and as the air is flowing continuously through this bike engine, what will happen? The heat from this plate is transferring into this air, and because of this the temperature decreases. You got this thing or not? So that is one thing if there is plate, and some scenario are there when there is no plate. That is also a that is unfinned heat exchanger. This one is finned heat exchanger. Okay, plate type, or it is also known as plate type heat exchanger. So no need to mention this thing. But these types of plate heat exchanger or finned heat exchanger are not necessary, are not that much important compared to your point as compared to the topic that has been taught. So you just follow mainly basically two types of heat exchanger. One is parallel type, one is counter flow. Parallel flow, why it is called parallel flow heat exchanger? See, the red light is from the left to the right. Similarly, from the shell side, it is from the left to the right. Got it? So that's why it is known as parallel parallel heat exchanger or parallel flow heat exchanger. Whatever you want, you can use. Arey. So any confusion up to this, please let me know. So I am drawing the next type of heat exchanger, which is your. So there is only one pipe. So it is single pipe heat exchanger. There can be multiple pipe. Okay. In some cases it can be like this na. This is your inlet. This is your outlet. So the heat is flowing like this way. Okay. And through the pipe it is flowing in this way. The red indicate hot fluid and the green indicate. So up to this I hope it is okay. I represent the heat exchanger as HE. Okay. So so the thing is that now I have to draw the temperature profile. I will try to draw the temperature profile. If this in the first case, which one is the hot side? The tube inside is the hot side, right? And the shell side is the cold side. So remember this thing. Similarly here, this one is the hot side and this one is the green one is the cold side. Hot side. So now the question is that if I draw the temperature profile, so this one is this end and this one is this end. So if I talk about the hot side temperature, if its temperature is say TH, I represent it I or 1. What I represent? In the inlet is I and outlet is you can represent it 1 2. It's up to you. So this is hot inlet, hot outlet. So can you tell me temperature of which one will be more, hot inlet or hot outlet? Hmm? So what will happen to the outlet? Its temperature will decrease. So if it is starting from here, the curve should be in a decreasing fashion. You say. क्या हो रहा है? Disturb कर रहे थे. Sorry. There is some issue maybe. Let me rectify this one. Now I think it is okay. So if this is THI, so this one will be your THO. So this is your hot fluid, right? Direction should be in this way. So now this is for the hot fluid. So what about this cold inlet? Say in this inlet it is cold fluid na. So for the cold fluid the temperature should be TCI or that one will be TCO. Okay. So if TCI start from here, definitely TCI should be less than TC1. Sorry, TH1. So if this is your TH1, TC1, and this is your TC outlet, TCI or outlet should be more than TCO. So it should be somewhat. Yes, sorry, this one is TCO. Clear? If not, please let me know. Because hot temperature releases heat to the cold temperature, and because of this, it's value will change. Similarly, as the hot water is supplying, how it is transferring? See, this red indicate the inside tube heat transfer. So the inside tube, the heat is transferred to the outside fluid. That means the temperature of the outside fluid will increase, as represented by this graph. So I hope it is clear. So can you draw this for the counterflow? Please draw. I am giving you 1 minute time. After this, I'll ask question. Actually, I have a back pain. That's why it is quite uncomfortable for me to sit today. So have you drawn this one? Hmm. So just check with me whether it is correct or not from your side. So if I draw the same thing here, if this is your profile, if I draw the from the red, see from the red side, that the hot water is flowing from this one. So just if I represent it as T H I and this one will be T H O. Similarly, if it is your T C inlet, it should be T C outlet. So as the hot water is moving in this direction, it will be its temperature will decrease definitely, right? So this is TH1 and this is your THO, right? So now tell me this TCI start from which direction? Left side or right side? It start from right side. So see here from the right side, what this indicate? This indicate the temperature gradient. Temperature is though temperature gradient is there. I am talking about whether temperature is decreasing or increasing. What this red light indicate? Decreasing. Yes, yes. So you say that the temperature TCI. If say this is TCI, So what will happen to Tc naught, Tco, whether it will be less or it will be more? So if its value is here, if it is a straight line, it will be here, right? This will be Tco. So it will be for your counter flow. So what student get confused? Students see that if the profile is same, that means it is parallel and this is counter. So this is not correct. So the parallel line in here this counter flow. You got it? So the arrow is in this direction and it is opposite direction. Based on the arrow you can say. So that is how the profile. Now tell me one thing. So either TH1 and TC1 can be equal. I am saying in these cases, in the left hand side cases, that is for parallel flow heat exchanger, either TC1 and TCI can both be equal. Why? Yes, which principle told this thing? Fourier's law. And if I talk about the thermodynamics, second law, good. So that thing is clear. Now, similarly, can THO and TCO be equal? Why? In the outlet, there will not be heat transfer. Yes. And now tell me about this scenario. Can THO and TCI be equal? THO and TCI? No. Uh, So can you now tell can THI and TCO be equal? It can be equal. Why not? Even TCO can be greater than THI. Can it be possible? It depends on the mass flow rate. If the mass flow rate of say if the hot fluid flowing through this region, if its volume is more, and in that cases it can happen na. So how to understand whether this thing is happening or not? That is the question, right? So see, as the if I talk about this curve, so the heat is transferred from the hot side to the cold side. So if its direction should be in this way, right? This should be Q. If I talk about this Q, what is Q? M C delta T. So if it is hot, this is hot fluid. So this is M of H, C of H, and what should and delta T means the temperature drop. So what should be it? It should be T THO. So how much heat at the beginning and at the end? Whatever temperature drop. This whole temperature has been utilized as an heat as heat, right now. This temperature drop. How temperature drop means gradient. As I have from the Fourier law, we know that the temperature drop mean gradient. Gradient means heat flux. So or more probability I can say it is heat, right? Similarly, just tell whatever the heat release from this from the tube side, it has been getting transferred to the shell side. That means the heat will be received by the colder fluid, right or wrong? Huh. So that means in the colder side, if I take that means the heat similarly in this formula should MC. cold fluid Cc into that means temperature increment minus Tci. So see, some students get confused. Like some students know that temperature should be final temperature minus initial temperature. Yes, it is right. I am not saying it is wrong. If it is final temperature minus initial temperature, if you take in the first cases, Tho minus Thi, what you will get? You will get negative, right? So what is negative heat indicate? That the system is releasing heat. And if it is plus symbol, that means the system is gaining heat. So that means if you think this way with respect to thermodynamic, it is also correct. Okay. Similarly here, if what will be the Q? Same formula. So now the question is why this equation is quite important. Please remember this equation because this is quite important, at least for numerical. Like in some question, you see how many variables are there. In the whole, forgot about this Q. Only just look into this MC part. I'm talking about this part. So how many variable you are observing? So total how many variable in both in this equal to this equation? Huh? Huh. See, CH. CH mean specific heat. Specific heat of a fluid is constant. Any fluid, it is constant generally. So Cc is also constant. Right or wrong? That means it is for hot fluid, it is for cold fluid. This is different. Like if it is water, for if both it is water on the cold, shell side it is water, on the tube side it is water, then it can easily get cancelled out. But if it is one side it is water and another side it is methanol, ethanol, then it is quite different, right? So if I consider for water, say for water, CH and CC will cancel out. So how many variables are there beside this? In the left hand side there is mH and two temperature. In the right hand side mc and two temperature. So ultimately six variables are there, right? So in general cases, if you think of an heat exchanger, what parameter you should know? You are just giving initially if I think I am just giving mass flow rate, mH will be no because in the tube side I can operate by manually. In a device by opening this electric circuit I can set the mass flow rate. So this mass flow rate is a constant general case, right? So mass flow rate of coal side is also a constant, but the constant not a constant is a given parameter. Okay, so if it is a given parameter, so then how many variables are there? Four variables are there, right? So when operating a heat exchanger, what do you think? Which of these four temperature will be given? Which side? Inlet or outlet? Inlet, because we are maintaining this inlet temperature. How? Say I am just talking about this side, the out in the shell side. If I am just applying water, normal water, right? So normal, what is the room temperature? That means at room temperature. So you know the inlet temperature, right? And in this side you are just supplying hot water, say at 80 degree. So what you know? You know inlet temperature, right? So if inlet temperature in these both cases are known, then how many variables are there? Two variables. That means the outlet temperatures are variable. So In certain cases, say this thing, this shell can be more, but this is a single pipe. If you put a thermocouple in this single pipe, what you will get? You will get the output temperature, right? So if you get this outlet temperature, what you can do? You can cold side, because sometimes what we do, we just measure thermocouple. Why this is essential? Say I put a thermocouple here, right? It will give the outlet temperature. I put a thermocouple here, so it will get the outlet temperature. So what will happen? How we will check whether there is heat loss in the system or not? So as you have told that if this temperature is known, you can easily find TCO, right? So from this equation, if you find TCO, and from the thermocouple reading, if you find this TCO, if both are equal, that it indicate there is no heat loss. But if there is temperature difference, what it indicate? That there is heat loss. Is it clear? Whether this concept is tough or okay? So up to this it is okay, I think. Huh? Okay. Hmm. That is the okay. That is 10 variable. I know it is also not wrong. But the thing in I am talking about gate perspective or a numerical perspective. Generally, in numerical perspective, only these six variables are there. Maybe maximum of six variable, but never you will find six variable. Only five variables are there. Only one is dependent. Five constant is given. One is dependent on other parameter. That means one parameter is missing, and you have to find out this missing parameter. Got it? Okay. And now, after before coming into this concept of LMTD, I am just showing you something which you require. Just let me check what are the concepts there in your syllabus. Huh. So I am taking a common example. Say this is a plate, okay, thin plate, metallic plate. In one side there is a fluid. In another side also there is a fluid. So this one is fluid 1 and this one is your fluid 2. Got it? So I am just giving the temperature value. If this is TF1 and this is TF2, let us assume TF1 greater than TF2, right? This is a metal plate. So what will happen? How the heat transfer direction will be in which side? From top to bottom or bottom to top? TF1 to, so that will be the direction in which your Q should be, right? Now you tell me, in the first few classes, first two to three classes, you have studied about what this is called, conduction. So now from this conduction concept, you just tell me one thing. if say before this I am just giving, if this one is your R1, okay, this one is your R2. So you know what is Q? Q is T by, say this is this, and thermal resistance is there, but this is a fluid, so there should be, initially there should be, for this, from this fluid heat is transferred into this solid, but through which mode? Conduction or convection? So initially convection will be there. So H1 I can write. So what will be the value? Just tell me. This equation you remember? Thermal resistance. Which shape means? No, it's a plate. Just assume plate. Like I have just, you just, I am, what I am asking, if this one is H1, this one is H2, if this is heat transfer coefficient, just tell me what should be in the bottom part. That is my question. You just forgot conduction, I think. No, total you just forgot, I think. Q equal to 1 by H A. Can I write? So that one would be H1 by area of this surface, this inside surface, A1, plus, say this is a rod. If I talk about the okay, for your understanding, what I do, I just make this as a rod. You're getting confused. That's why I'm drawing this fluid, and this fluid is flowing. Okay, and this one is a small cylindrical pipe. So now got this problem. So the heat transfer should be from a cylindrical perspective. It should be. You remember this thing? Uh, Very good. ln R2. R2 means outer radius. R1 is inner radius by 2 pi KL plus initially convection, then conduction, then again convection. So 1 by H2 into maybe equal. General case it should be equal, but let us assume this is the inside surface, this is the outside surface. This is not a cylindrical surface. For cylindrical surface, but some portion may be insulated. So in general cases both is equal, but I am not considering. Okay, is it clear? Huh. So that way it is quite important. Now you just tell me one thing. What is the formula of Q? Q equal to, if I can write, can I write Q equal to H A delta T? You remember? So that H is a, see there is H here, and a conduction is there. So I am just represent this Q is in a term overall heat transfer coefficient U. So I can write Q A R reference into T final 1 minus T final 2, F2, sorry. U is the So it is a term that is used to represent these all these three in a single term. Overall heat transfer coefficient. Right? What is a reference and why it is important? So why is a reference important? Say if someone is taking the outer surface for calculation, then he have to take A2, and if someone is taking the inside surface, then A0. Right? So now the question comes, in that cases the value of Q should be different, right or wrong? After this it is clear or not? Just tell me. So I am saying, so A reference, that means if the value of A changes, so what do you think? Q will be changing or not? My question is A reference. What is A reference? A reference means the area. Area means whether you are taking the inside area or outer area, that thing. So my question, another question is that if the area, if I take outside area, uh, what will happen to Q, and what will happen to Q if I take the inside area? Whether these two value are will be equal or not. And other see F1 and F2, I just assume it is constant. So it depends on you whether Q will be same or not, right? So the thing is that if I compare these two terms, this equation and this equation, can I write this equation as Tf1 minus Tf2 by 1 by U, right? So can this thing be written as 1 by U A reference should be 1 by H1 A1 plus ln R2 by R1 2 pi KL plus 1 by H2 A2. Now the thing is that if I have to find U, say I am taking inside area, so it will be A1, right? So I can write H1 A1 plus ln R2 by R1 by 2 pi KL plus, so you can cancel A and you will get U, right? Similarly, you can also take one thing, this is one. Next case, what you do, you can take a reference as the outer area. Same equation, and after that you can find yes or no. So just tell whether any confusion after this, else I'll move to the next one. If you want to note down something, you can note down. I'm giving you 2 minute time. Please let me know when you complete note down of this. So this thing, whatever I am discussing, this is based on the numerical approach. If numerical question comes, how you need to solve this, that is the thing I am showing. So in this way you can find U, right? In the question value will be given. There is nothing assumption. Okay, that is a daily life problem. See, if the thickness of this plate, if it is small, then R1 and R2 are almost equal. So at that cases, what we do, we just ignore the middle term. If R1 R2 almost equal, then this should be 1, ln1 is 0, right? Okay, so that is it. Just a minute. So you know how to get this U. Now the question is where you have got this thing. Just let me check. Actually, it's the last class now. So, huh. So this is normal cases. So in that normal cases means water is flowing. There is no such problem in this system. So another thing can happen in a heat exchanger is that the water is flowing. So generally the water that we found in our household contains certain minerals, certain scaling factor and many things, many impurities are there, right? So if you see, if you take a bucket of water and kept it for 1 week, you will see certain colorful particles just deep inside, just settle in inside this vessel, right? So what is this thing? These are actually scaling or fouling effect. So similarly, even heat exchanger work on a certain fluid for a long period of time, what will happen? The tube surface is covered with a with such certain types of material or I can say then insulating material, which is also known as scale or foul. So what do you think? What will happen if the tube surface is covered with certain impurities or dust particle? What will so if its thermal resistance will increase, what will happen? Huh, yes, good. So that thing I will show in the next one. So up to this it is okay. Hmm. So there will be fouling. Fouling basically is the settlement of scale and other dust particle or impurities over a test section or a heated surface. Okay. So see here each and every term I can represent it R convection, R conduction plus R conduction, right? Actually it is resistance, thermal resistance. So I am just doing one thing. I just represent the thermal resistance due to this fouling as Rf, which is also known as fouling factor. Okay. So fouling factor basically, if I write RF, it is actually what is the fouling? This indicate the resistance. If I talk about this thermal resistance, what is thermal resistance? Actually, it is the inverse of what is thermal resistance? Heat transfer coefficient. So I can I write here it will be U. U is the total heat transfer coefficient, but the total heat transfer coefficient should be this one is said right is dirty minus 1 by U clean. So that means because that the resistance because of dirty or tube would be more compared to resistance because of the plain tube, right? Hmm. So in the above thing you just see I write 1 by U A reference. This thing I have right now. So now can I write 1 by U dirty into A ref. So I am just writing for a one case. 1 by U dirty into A ref, say what I write, say AI for A1. So that would be equal to just tell 1 upon H1 A1 next. Huh. But the thing is that in this tube, this is the material na. There is a certain insulating layer form na. Also there is an insulating form, layer form. So that insulation form term can be counted. So what it would be? It would be RF1 inside side by area. Yes or no? You got it? Plus, see, first convection, then resistance due to insulation, insulating material. Next, conduction. So that would be ln R. uh, okay. Next, so there is RF2 by. Next, 1 by H2 A2. So this is from this you can find out 1 by U dirty, right? So 1 by U dirty if you find out, can you find out U clean? This is your U clean. So ultimately if you subtract this thing, you will get to know how much the heat transfer is lost because of fouling. Got it or not? So this is the main concept. So see, this heat exchanger concept is quite long, so I will be explaining it into part because that will be quite helpful for you. So just one question up to this, as you have understand this thing. So I am just giving you one question. Check the question. I am giving you 1 minute time to think and answer. Why it is true? What I say in the counter flow, you just maybe see if this is the curve. This is counter for curve, na? So I what I say if the fluid is flowing in this direction, right? So the question is that the cold fluid output temperature can never be greater, like this types of question, na? Just read the statement. You have the statement? No, I think. Huh, huh. Outlet temperature. See the if I talk about the cold outlet, that means this temperature. They are talking about this temperature and this temperature, right? So what I say if the volume of this fluid through the tube side, if it is quite more. If I talk about m dot c, okay. So if it is more, so what will happen? The heat transfer from this side to this transfer will be less. That means the temperature drop will be less. If the volume is more on the tube side compared to the shell side, that means the colder side will take less amount of heat. Sorry, the colder side will take more amount of heat compared to whatever with the heat transferred to the cold side, right? So that means its temperature may increase more than this thing. Yes or no? But here, in that cases, if you see the temperature is say 100 degree, right? If it is 100 degree and it is say 30 degree, you just look into this thing, 100 degree and 30 degree. So what will happen? It temperature gradually decreases 80 degree, 70 degree, 60, 50, 40 like this, right? And here it will goes on initially once it is coming in contact with this fluid, as the temperature is quite, the temperature difference is 70 degree, quite more na, 130, there is 70 degree. So if the temperature gradient is more, that means heat transfer will be more. So already the liquid will initially take up more amount of heat at this side, right? But here I will just consider, give you an example. Say this is 100 degree, same condition, and this is 30 degree. So at this point, at the initial point, what will be the temperature of this fluid? It will be like that. That means more than these cases. Here it is 30 degree, here it is 100 degree. So what will happen? Initially the temperature difference is more, so the heat transfer will be more in this region. But here if it is say it is 80 degree or 70 degree, that means the heat transfer will be less, right? So initially the liquid is taking heat from this region. So it may happen 30 degree at this point its temperature become 80 degree, 60, 70, 80, 90, 100. Up to this, at this point it is already getting 100. And even it is getting 100, more than 100, because it taking up the temperature from here. So what will happen? This temperature can drop. Yes or no? You got the difference. So the statement will, the cold fluid temperature can be greater than the hot fluid temperature only in case of cross flow or the counter flow heat exchanger. Got it? So correct answer will be option false. Okay. Now I am moving to next thing. Hmm. So fouling is okay, I think. So see, this fouling condition or this scenario, you just look. You got to know you have the area A2, A1. This is the area you know, and radius and all these things you can know. You can find out the U. Okay. So now if I talk about heat exchanger, in heat exchanger, which area you will take? I am drawing an heat exchanger. Say any type of heat exchanger I am drawing. This is an heat exchanger, right? So the question is that the equation that I have already written earlier, how can I apply this equation? Can I write this equation in this case of heat exchanger? Here there is TF1, TF2, right? What I consider TF1 means here throughout the domain this temperature is TF1, it is TF2, like this way. It may change, but in a heat exchanger, what will be the TF1 and TF2? That is my question. Please check and let me know if you get this thing. Which area you will take? Area of the hmm, Q. So see, I just consider your case, whatever you said. That Q equal to I know A reference into temperature difference, right? What is the temperature difference here? Because throughout the fluid is changing throughout the domain along the length, right? And here also it is changing. So which temperature difference you will take? Because there are many temperature TH1 if it is in a hot fluid, this is THO, right? And if I take this one TCI, TCO, and again I am drawing this profile for you understanding. This is THI, THO, this is TCI, TCO. So which temperature you will take? So that will be question, because I can't say that this can be the temperature or that can be the temperature. You got my have you got this thing? So why? Why not THO and TCO? Because see, if you take THI and TCI, the temperature difference will be more, and if you take this to the temperature difference will be less. So that means you can have to take a minimum, or you will take an average one value, right? So that thing. So for this, I am just giving you an. I am just taking a small area here. Okay. So you just know what is a formula, general formula I have written earlier. There should be an energy balance. What is the energy balance equation in the previous class? Okay, I just write. So you got Q equal to M, MH, CH, equal to, okay, this is these two are equal, you got it, right? Now in this small section, if I take this small section, okay, in this small section, say the flow is in this direction from this side to this side, right? So this is the direction. So in this direction, if I take the heat dq, small heat, it would be mh ch into a temperature difference in this region. So that will be d dth, right? So this dth, what is the whether this is plus dth or minus dth? Because the temperature is because the temperature is decreasing. Similarly, this heat, whatever the heat loss from this hot side, it will be gained by this cold side. So that should be equal to mc cc into d. Can I write? Any confusion? Just tell me. I am just showing you the derivation, a derivation for this one. Okay. Huh. So now what I do, I am just writing the same derivation. I use another color. So if I write dth minus dtc, what I'll get? Just the temperature difference between the hot side and the temperature difference between the cold side. So yeah, from this I can write na dth is minus dq by m dot, right, and dtc is dq by, so I take dq 1 by mh. Please remember this derivation, it may be important. If numerical question doesn't come, then it is important. Okay, so you got, and this thing, this is so can I write? Can I write this thing? So now my question is that I have written all these things. So you just tell me one thing after this. What is MHCH? Huh. So from this part, can I write MHCH value? Can I replace? So what I can write? 1 by MHCH is, so see, THI minus T THO by T plus by Q, right? So now see, the thing is that if I write minus dq by q, yes or no? Just check. If there is any issue, let me know. Any confusion? I think I had done mistake somewhere. I'm just checking this thing again. Right, this thing. Huh. So see, this small q, Can I do one thing? This thing, you know this thing, q equal to this. If for a small reason, if I have to write dq, what should be dq? Because I have to find u, overall heat transfer coefficient, and so I can write this one u into this one is temperature difference. So that should be your Th minus, can I write? Yes or no? See, that means this thing. So one thing is that from this thing, and another thing I just have to generalize this thing. That's why I'm writing this thing. Okay, it is not an issue, that much issue. So in place of this one dq, can I write in place of dq what I'll get? Because I have to write it in terms of u. So I can write minus u dA Th minus Tc by this q will come into Th1 minus Tho plus Tco minus Tci. Okay, yes or no? So if you integrate this thing, this Th minus Th term comes here. So I just shift this term to here. That's it. Next line I am just erasing this thing and write down this on that side. Th minus Tc. What is that would be? This is, what is this integration? Ln. This is L, this will be Ln na, into minus this one be area integration into this whole this term, right? So now the thing is that this integration is from inlet to outlet. Initial value is inlet, that means I can take I, and this one will be outlet, right? Because I am not writing a constant here. That means whatever I am saying, that this one is I to O and this one is similarly total area I to O. So our main motto is that for a given question, this thing is given. So I just erase this thing. Can I erase? So ultimately what you will get, this will be your ln T H O minus TCO by T Hi minus Tci, right, equal to minus UA by Q into Thi. See, I am doing one thing. I am just writing this in the same fashion. Tho plus Tco minus Tci. Can I write? check this thing. Up to this, if you have any issue, please let me know. Okay. So now can I write Q? What is Q? This Q is your U into A, right or wrong? Please check and let me know first. Into UA, right? And what should be the in the top? This value, hold this thing, and the bottom there should be ln. This thing, this outlet value na, can I write into del T outlet by del T inlet? Can I write temperature difference outlet of the both side and inlet of the both side? So now I have to represent this in terms of see THO and TCO. There is negative sign here. So this thing can I write? The minus sign is there. So if the minus sign goes here, uh, so you observe this will become TCO. Say minus minus plus. This one is minus. Okay. Again, this one is minus. This one is plus. So can I write TH1 minus TC1 I? This is one A. This is I. So that means your UA into del T outlet minus del T inlet by ln del T outlet by del T inlet. Okay. So this thing, what is the formula of Q? Q equal to UA. General formula is Q equal to UA temperature difference, right? So this temperature difference is known as your LMTD. Okay. Log mean temperature difference. Logarithmic mean temperature difference, this is known as. So please remember this thing. So it is not right, like that someone can write outlet minus inlet. If you write inlet minus outlet, then it should be above one is inlet, bottom one is outlet. So it's depend up to you which value you are taking. So but remember this LMTD. Okay. So I think it is clear. Huh, huh, till. Hmm, 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 hmm. Uh, so you only LMTD is okay. So not necessary to write Q. Okay. So now the thing is that the problem whatever I have taken, this is for which flow? So can you write it for parallel flow? Sorry, can you write it for counter flow? So what should be the difference? So see. Hmm. Hmm. So the thing is that only you can observe from this graph. This one is T. If I talk about this TO, that means the temperature difference between these two ends, right? And if I TI, it should be the temperature difference between these two ends. In the parallel flow, I'm just writing this thing again. So LMTD is ln, sorry, what is LMTD? This one is your del T O minus del Ti ln del T naught by del Ti. So in case of your counter flow, what is it? So this one is your Thi, this one is your Tho, this one is your T uh, T C I T C O. So this one basically represent any side. If you take this side, only this side and another side, the difference is from this graph, not from inlet outlet. You remember this thing? So the best thing is they do not remember by I 0 and O. So that will create a confusion. So the standard way to represent is that represent it by 2 and 1 and 2 or 2 and 1. So you got it? So basically the derivation that I have done is based on your counter flow. The same thing if you done for this parallel flow, you sorry, I have done for parallel flow. You can do it for counter flow. So what is the basic difference in the counter flow? This thing will be, see, if I talk about this thing, this equation, this one is negative here, right? And this one is positive. Now in the contour flow, in the cross flow, this one is negative. This will be minus del H, and this one will be no. You see, the arrow is in this direction, but though the arrow is in the same direction, but the temperature is decreasing. That's why negative. Here, yes, you see. Here, the case is that though the temperature is increasing, but its direction is, so it should be negative. So in this way, if you derive, you will again get the same thing. So the student, sometime in the question exam, they can ask, derive this for counter flow. The same thing. Please derive this at your home, and please let me know if you are able to solve this one or not. Okay. This is simple derivation that is quite essential. So why the LMTD method is necessary? Basically, in the LMTD method, you have Q equal to U A LMTD, right? So basically, this A is not known to us. Generally, you know Q, you have U, you can find out the LMTD for all this temperature value. Then the area you can find out. This area is the design parameter. Okay, is a design area, not the actual area. It is a representation. Like if this is an if I say what is the model, what is the model of your laptop, you can say that my model is say in my case it is an Apple, so my model is, I say that it is M2. So from this M2 you will get to know, yeah, this is this feature, you can assume by yourself. Like similarly, if you can find out this area, you will get to know, yeah, that means the heat exchanger should consist of this much of tube. There is a what I can do, there is a book. What book it is called? I just forgot the name. Data book. There is a data book. In the data book corresponds to some certain value. You will easily get to know how many tubes should be there, what is the diameter of the tube, and what should be the diameter of the shell, and all these things you can easily find out. Okay. So there is a name of this one. Which convention? I just forgot this name of the convention. Tema convention. This is known as Tema convention. So that's why area is required. So LMTD method, in LMTD method, what we know? In LMTD method, all other parameter, LMTD method is basically means to find out this value of A. Got it? So another method is there, which is your NTU method. Just a minute, let me check whether LNT method is yes. So LMTD method is over. In the LMTD method, actually it is based how you calculate what is required in the LMTD method. You require uh, at least you need to know the either you know all the four temperature or you need the temperature difference between both these two n, right? Depend on cross flow and parallel flow, you have to check. Mainly the temperature difference is required, right? And also you should be given q, given you can easily find area. Your objective is to find area. Okay, so where area is not given you in this problem, or where the design parameter is not given in this factor, you can use this LMTD. And another method is that NTU method. Okay, or effectiveness method. It is also known as NTU effectiveness. Okay, why this method is necessary? In this method, you can know the rating. That means how much the heat exchanger is capable of transferring it. Like I know that if I say an example, I know that Ayush is able to do 5 works in a day. This is your capability, I know. So that doesn't mean that every day you will be able to do 5 works. In some day you will be able to do 4 works, right? So that is your efficiency. So this NTU effective method is necessary. In this problem, you will get to know effectiveness. Okay. So effectiveness, what is the definition of effectiveness? It is Q actual. Q actual, you can find out Q, right? What is Q actual? How will find out Q actual? Anyone you can use. You can use Q actual equal to MC AC. Just any cases you can find. T, what is this value? THI minus THO. Yes. THI minus THO. Not HI, it is C. It should be C, na? Okay, I just have written it wrong. This is MHCH, and I can write MCCC TC outlet minus TC inlet. That types of formula you can find. And T max, what Q max, sorry. Q max is basically among these CH and C2, whichever is mean. CC. You find out this value, whichever is mean. So you have to take this value. That means C minimum of these two value you have to take. And minus temperature difference. That means hot inlet minus T cold inlet. Why? Hot inlet minus cold inlet. See, this hot inlet is in this direction, cold inlet is in this direction, right? So heat transfer will be more if in the whatever be the, say I'm giving you an example scenario, just in this cases, say this and not this case, THI, if this is 100 degree, right, and this is 50 degree, so the temperature drop is 50 degree, right? And temperature drop will be maximum if it is at 100 degree, because whatever be the temperature at the ending entry point and in the cold side, if the entry point is same, then the temperature will be maximum, right? I'm just giving you an example, not this point. Just sorry. Sorry, it is at 50 degree. Can I make mistake? I have to check. I think I have done a little bit mistake here. Just a minute, huh? Let me confirm this thing. Hmm. Ah, yes. That means not 100. This should be 50 degree in this case. If both this temperature is same or zero, that means in this cases the difference will be maximum, right? When it will be Q max, if this difference will be maximum, yes or no? But if say if the cold side, if the temperature is 40 degree and it is 50 degree, that means heat transfer can happen here, right? But at that cases, your temperature, your Q actual should be less, because you have to take see. I am just giving you an example that CH and CC, that should be different. So if that is different, so if it 100 degree, it is 50 degree. So you can calculate, you can easily find out the value would be 50. You will get a difference, a temperature difference. Say in a given cases, it is 40 degree and it is say your 90 degree. Okay. So it should be, the difference should be 50 degree. So m dot c will get a value, it should be 50 degree. Um, so the basic difference, if mh and mc both are same, so that means ch and cc should be same, right? Huh. So it is okay. Now you see this c mean among these two value, if someone is small, why that will be taken place? Because if the specific heat will be less, so it will take up the more amount of heat on the other side. If a certain fluid, you got it now. So that's why if the temperature difference at this say 50 degree, that means these two curve converge. If these two curve converge, then whatever be the heat transfer from the hot side and whatever be the heat transfer from the cold side, that should be maximum. Because if it is 50 degree, the difference should be 40 degree, right? But the cc value you can take, so accordingly it can get compensate. So basically that is the fundamental here. That means qmax is basically hot inlet minus cold inlet. You just remember this thing. Okay. So so if you know the inlet temperature only, you can find out qmax, yes or no? In the question they can give you efficiency. So if they can give you efficiency, you can find q actual. So in the q actual, you know the inlet temperature, right? So you can find out the yes sir. Or another thing is that if the outlet temperature, any of the outlet temperature is known, you can find out efficiency. So NTU method, NTU basically is your UA by C mean. In this thing, say in the previous case, our objective was to find design area, right? But here our objective is to find Q, not area. Our objective is to find Q actual. Sometime in the question NTU value will be given, U will be given, A will be given. So what you will get? C mean. If you get C mean, you can find out Q max, and you can find out Q. So that is the basic difference. So a question you can expect in the exam: what is the difference between Q LMTD method and NTU method, and when this method are used? Please go through this method, and please let me know in the next class if you understand this thing, or it requires certain things from my side to give you. So the main thing is that LMTD method is for design parameter and NTU method is for rating parameter. Which one is simple and which one is complex? Just tell. Because from your understanding. Hmm. No, actually, the reverse one is correct. LMTD is quite easy, but NTU method is slightly complex because the formula of NTU changes. Like I have written NTU equal to UA by C mean. For different heat exchanger, different NTU formula is there. So that's why this thing is different. But in the LMTD method is same for everyone. Okay. So that's why I'm asking this question. Mm. Yeah, okay, it's a good thing that you also check one thing. Why LMTD method is mainly preferred for contour flow, not parallel flow. This question, please go through this question. In see, this LMTD method is good for both too, but LMTD method is generally people used for contour flow only or cross flow. Okay. This is basically mainly why this thing, because in the control flow you see the temperature difference is uniform almost, right? So as it is uniform, so that's why the efficiency, see, if you are doing a work uniformly, you can do it for a longer period of time. But in the previous cases, in the parallel flow, you see the curve converges at a point. That means initially the heat transfer will be more, and after a certain period, the heat transfer will be less. So if a system is there that initially it gives like it's a cricket match. If a player comes to the crease in the first 6 over, he has strike a lot of run, and after that he is playing a dot. So ultimately what it indicates? It indicates he is not that much effective. But if you look into the innings of Virat Kohli, what he do? He can initially build his innings. So that means you can already always see that he continuously score runs throughout his period of stay. So that is a consistency. So if there is consistency, so that means the efficiency will be more. Okay. So I think though there is some numerical concept, few questions are there. Uh, it will be better if you explain in the next classes, because already today I have a back pain also. So and you uh, so that is the thing, and few more minutes. And what about this question that you have asked me today? So up to this, is it clear? So in the next class, what we will do, we will discuss some concept, numerical question regarding this, and what are some of the important thing that you need to understand, that you need to know from the previous one, that is required. So please, in this concept, there is an important concept. The concept is that please go through this difference between this NTU and LMTD method. Why? Even in the interview, if you go for some placement, so they will ask you when we will going to use LMTD method and when we are going to use this NTU method. The LMTD method is used for design criteria and the NTU method is for rating purpose, but you have to tell in details. So sometimes they can ask which method is good, like this counter flow or this parallel flow. The cross flow and counter flow both are same. Parallel flow is different. Actually, it's a significance. That the significance is that in the say in a heat exchanger, like in a real, if you take any normal problem, the heat transfer rate can easily found through temperature gradient. Because if it is a conduction, so you can find through this heat temperature gradient, and if it is a convection, you need only temperature drop nh, right? But in an heat exchanger there is, it's a there is two fluid required, right, for heat exchange. So that is a rapid change in the phenomena happening. So as the rapid change in the phenomena happening, so you can't tell about the how much heat transfer is happening and what are the thing. So you need to represent it by a normalized unit. And that unit is LMTD and NTU. Like you are in a class where if I have to ask about what is the height of the student in the class, can you tell he is 5 foot 6 inches, 5 foot 4 inches, 5 foot 1 inch? You will not tell like this. You will say that the average height of the class is 5 foot 5 inch. Like it indicates that some people may be less, some people may be more. But on an average scale, if you take 5.5, most of the people are near about to this scale. Okay. So similarly, this LMTD method basically represents that it is a representation which indicates that the temperature drop along the colder side and the hotter side are almost similar. Say if you check if these two things, del T and these two are equal, what will happen? If the heat transfer will not happen. You got it this thing? And say if somehow this T1 is less compared to del T2. So what will happen? So overall this value will be more, right? And if it value is more, then means LMTD will be less. That means Q will be less. So it depends on the again if I take if del T2 is less, okay, compared to T1. So ultimately this term will be very less. So what will happen? So you can easily understand the phenomena. Like this way you can tell what is the changes you will get and what should be the temperature you need to maintain to get high heat transfer coefficient. Like if you have to make a compact design you means you have to utilize less area. So you know you have a target, say you know that you will require U of this much 400 or 500, and you know this Q. So what you need to do, you have a certain value Q, fixed value of Q and fixed value of U is there. You have to reduce area. Okay. So what would be A? A is Q. So basically, if you need to reduce area, what you need to do, you need to reduce LMTD considering other two parameter. So that's why this parameter is important to if you have to make small system or larger system. Accordingly, you have to change this value. Hmm. It's a design area, not the actual area. Okay. Huh. Design actually see it is like a constant. It's a, like a number because certain if the design area is coming this value, that means what I say that the area that the diameter of the pipe should be this, length of the pipe should be this, shell size should be this. It is corresponds to a value on the data book where you will get all these parameter. Okay. Next another thing, similarly is the NTO. NTO is reverse case. So if you have to check whether the system is efficient or not, if the heat exchanger you have designed give you good efficiency, 80% efficiency is there or 90% efficiency is there, then in this the method is required. Okay. Just tell me the previous cases. One thing, control flow you have. Uh, First I have to have parallel flow. Okay. I'm just asking you to answer one question based on the previous class. It will take hardly 3 to 4 minutes to answer. Say A, just say hot fluid. This is hot. Okay, not hot. Uh, I just give you an example. This is saturated water. Saturated water means or saturated liquid. What is saturated liquid? It means it is at the boiling point. That means throughout this point the temperature will be close, it will be 100 degree. So I am just saying that throughout this domain it is at saturation condition. So if a cold fluid come in this way and moves out this way, so this is THI, this is THO. So at that case THI and THO should be equal, right? Because this is boiling point now. So what we know that if the this is saturated, say vapor, not liquid. For your understanding, I just convert it into vapor. So initially this is saturated vapor. So as you it moves through this pipe, so what will happen? This is cold fluid. So the cold fluid if goes, what will happen? It will convert the vapor into. So at what temperature a vapor is converted into liquid? At the same temperature. Phase change is happening at the same temperature. That means if it is at 100 degree, it should be at 100 degree. So that's why this line is straight line. But if I talk about this cold one, the cold one will increase or not? Because it is taking the heat from the vapor and latent heat from the vapor and converted into. So some people get confused. How without changing the temperature this graph increases? Because this is a two-phase phenomena and this one is a single phase phenomena. You got it? It's quite interesting. This is for saturated condition. So what will be coming? Which one? No, see, the shell side is a single phase phenomena, whereas in the tube side it is a two phase phenomena. So that previous thing, whatever I have explained, LMTD and all these things, this one is for a single phase. Always remember, LMTD and all these concepts are for single phase. Even opposite you can tell, if it is a contour flow, so how the graph will look like? Saturated vapor, saturated liquid. So if it is TH1, it would be this is TC1, this is TCO. So what I will get, I will get to know that if I draw the plot here, initially, THI would be equal to THO. Inlet temperature will come here, right? T, and it would be, got it? But this temperature can be more than this one. If this temperature, see, now you got to know if TCO greater than THI, that means at this side boiling start. TCO, phase change start. So that thing can happen only in contour flow. You got it? Why I have in the previous case I have said that this thing can happen. So is it clear? So this is up to yes, yes, boiler also the same phenomena. So now you got to know that LMTD, whatever I have said, LMTD NTU is for single phase purpose. But if it is a two phase purpose like the boiler, then these are the curve temperature profile. So please remember this thing. Okay. So this is for today's classes. So your problem, can I discuss it on the next class or it is urgent? So I'll discuss, huh? On the on the Saturday. So if you require it before this date, just give me a message and I will help you to solve this out. Actually, because of this, what I have said, because of this pain, I can't speak more. Okay. No, it is on Sunday. Actually, I am leaving on Sunday evening. Thank you. So we will meet on the Saturday. We will have some discussion on this problem that can be comes in the question or the important concept which is necessary. Yes, yes, yes. Actually, today is the last class, but that one will be extra class. So that's why I have just extended this. Actually, the last few classes it takes more time compared to the time allotted to us. That is anyway. Thanks, Anand. Then I wish. Uh, okay, bye. Next day I'll definitely discuss about your problem. Okay, because it will take time, and I require this chart also. I do not have the chart right now, so I'll definitely. Okay, okay, okay. Thank you. Thank you. Thank you so much. Bye.